Hello, AP Stat students. Today we are going to do section 5.2A and 5.2B, where we'll actually be calculating some probabilities. In 5.2A, we'll be talking about probability models and some vocabulary, and then we'll introduce a really important formula. Probability models. Luckily, we don't have to rely on simulations all the time to determine probability. We have mathematical models available to help us determine probability. Each probability model consists of the sample space, and what the sample space is it is the list of all the possible outcomes. The probability is the chance or the likelihood that each outcome will occur. An event is a collection of outcomes, a subset of the sample space. Here's an example problem. Below is the sample space of rolling 2 die. So there you have all the possible outcomes. If you count those, there are 36 outcomes. And these are fair die, they're not weighted. So each outcome is equally likely to occur. So the probability for each outcome is 1 over 36. Right. In this particular problem, using that model, using the sample space, what is the probability that the sum is 5? So remember that P, and in parentheses, the sum is 5. So in order to do that, we need to find out how many of the outcomes add to 5 divided by the total number of outcomes. So here is a 5. There's the sum of 5. 5. So 4 outcomes out of 36 total outcomes. We want to reduce our fractions, and even we can go one step further and write them as a decimal if we want to, because our brains like it with smaller numbers. It makes more sense to us. Okay, another important vocabulary is the complement. The complement of an event is the probability of an event not occurring. So it's everything but that event. So if the probability of probability E symbolizes the probability of an event, then to symbolize not E, you would put probability E with the superscript lowercase c, and that symbolizes the complement of the event, and I just call it probability not E. A complement of an event can be found by, and remember I had mentioned earlier that the probabilities add up to 1, so to figure out the complement, you would take 1 minus the probability of an event. So the probability not E is equal to 1 minus the probability that it is probability of event E, right? And so let's use an example, or let's use the 2 dice example. So what is the probability that the sum is not 5? So the probability that the sum is not 5 is 1 minus the probability that the sum is 5. So so that'd be 1 minus 1 over 9, which is 9/9 minus 1/9, which is 8/9, or 0.889 if you're asked to write a proportion. So that's how you use complements. All right, the next big one is mutually exclusive. So this is a really big one. Okay, 2 events are mutually exclusive if they cannot happen at the same time. And I'll give you a couple of examples. For example, you can you cannot have the probability that both of the dice are even and the probability that the sum is 5. Because in order for the sum to be 5, one of them has to be an odd number. So you have 2 plus 3, and then 3 or 4 and 1. So one of the numbers is even. So you can't have that happen because probably both numbers are even, and you can't have that those two get the sum of 5. So those two can't happen at the same time. Another example, oh, and by the way, I wanted to mention mutually exclusive means the same thing as disjoint, and you might have heard that in a previous class. So if you see the word disjoint, it's the same thing as mutually exclusive. They cannot happen at the same time. Another example is probability that you get an A in AP Stats and the probability that you get a D. Those can't happen at the same time. Either you get an A or you get a D, but you're not going to get both. All right. Two events are inclusive if they can happen at the same time. An example is what's the probability at least one number is 2 and the probability the sum is even. So if one of the numbers is 2, the sum could be even or it could be odd. So that can happen. So that is an example of inclusive events. And okay, for the rules of probability, all probability is between 0 and 1 inclusive. So greater than or equal to 0, less than or equal to 1. All possible outcomes together must have probabilities whose sum is 1. Now, the only times that you can get away with the sum not being 1 is if there's some sort of rounding error. And we'll look at an example in that instance. If all outcomes are equally likely, like in the fair die example, the probability of event A occurring can be found by, so the probability that event A occurs is equal to the number of outcomes corresponding to event A divided by the total number of outcomes in the sample space. If events are mutually exclusive, so here's our first formula here, and you'll see this on the formula sheet. So if events are mutually exclusive, meaning they cannot happen at the same time, then the probability of A or B is equal to the individual probabilities added together, probability of A plus the probability of B. And that's if they're mutually exclusive. If they're inclusive, this is the formula. It's just changed up a little bit. So the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And the reason why you're subtracting this is because there is an overlap. And I'll give you an example here in a second. So these are the two big formulas. And I don't remember which one is on the formula sheet. I believe it's the top one, but you just need to know to remember to subtract if there is an overlap, if events are inclusive. So to give you a good example of one, let's put one up here. So let's look at a deck of cards. So what's the probability that you get an ace or red? Okay, so I used to take for granted that students would know how many cards were in a deck, but there are 52 cards in the deck and there's 4 suits. So you have hearts, diamonds, you have spades, and you have clubs. So there's 13 cards in each suit. The hearts and diamonds are red and the clubs and spades are black. So in order to find the probability that a card is ace or red, you would do a probability that it's an ace plus probability it's red minus, but then you have that overlap where it's still one card, so you have to subtract that, the ace and the fact that it's red. So the probability that a card is an ace is 4 out of 52. And the probability that it's red half the cards are red, so 26 out of 52. And then you have to subtract that one card that's an ace and a red, so 1 out of, oops, 2 out of 52. So because there's 2. Because you're double counting them when you counted them in the ace and red and the red. So there's 2. But that's an example of when 2 events are inclusive. And you have to subtract the overlap. All right, let's do an example. For flipping coins, imagine flipping a fair coin 3 times. Give a probability model for this chance process. Now you can do a tree diagram, which we're going to do later on in this chapter, or we can just list the possibilities. So you can have a heads, 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 or you can have heads, heads, tails, heads, tail, heads, heads, tails, tails. You could have all tails. You can have tails, tails, heads, tails, head, tails, tails, head, head. So you can represent this with a tree diagram if it makes it easy. And this is a fair coin, so each is equally likely to occur. So the probability of each outcome to occur is 1/8. All right. Next example, AP Statistics scores. Randomly select a student who took the 2010 AP Statistics exam and record the student's score. Here is the probability model. So those are the score choice chances 1, 2, 3, 4, 5 on your AP exam, and those are the probabilities of each particular score occurring. Show that this is a legitimate probability model. So a legitimate probability model must have probabilities that are between 0 and 1. And if you look at all 5 of those are all between 0 and 1. So all the probabilities are between 0 and 1. And then if you add them up, I went ahead and added those up. I added the 5 bottom numbers and I got 0.99. So now you have to ask yourself, is this okay? Was this a rounding error? And looking at the values in our table, they are rounded. They are 3 decimal places. So you have to make a judgment call here. And I'm going to say it's close enough and that it's yes, that this is a legitimate probability model. Now, when would you say no? Well, first of all, if it's anything over 1, then that's not even possible. But if you're in that 0.01 ballpark amount, then that is close enough. So yes, so all probabilities are between 0 and 1, and add up to 1. Put a little question mark here because we decided we're going to say yes, even though it's 0.99. Find the probability that the chosen student scored 3 or better. So to notate that, the probability of 3 or better, so you could put 3 and plus. And so if you go ahead and add those probabilities, that'd be 0.235 plus 0.224 plus 0.125. And that would give us a grand total of 0.584. Or you could have used a complement and say, what's the probability that, or you can subtract the ones that aren't 3 or better. So subtract the scores of 1 and 2. So you can do 1 minus 0.223 minus 0.183, and you get 0.594. But here's the problem. Those aren't the same. And the reason why they're not the same is because we should have used 0.99 here. But we basically said that it was a legitimate probability model. So, I mean, it's not that much off, but it is off quite a little bit. Okay, in our last example for 5.2a, choose an American adult at random, define two events. Event A is the person has a cholesterol level of 240 milligrams per deciliter of blood or above. Event B is the person has cholesterol level of 220 to 239 milligrams per deciliter of blood. According to the American Heart Association, probability of event A is equal to 0.16, and I'm sorry, the two that I just read were just the events. Here are the probabilities. So the probability of event A is 0.116, and the probability of event B is 0.29. Explain why events A and B are mutually exclusive. So if you remember back to what mutually exclusive was, is they cannot occur at the same time. So in this particular case, in context, you can't have blood value of 240 and above and 220 to 239 at the same time. Say in plain language what the event, quote, A or B is, then find the probability of A or B. So in basic plain language, the cholesterol, the quote, A or B is the cholesterol level is between 220 and 239 or 240 plus. And what is that probability? So the probability A or B, and these are mutually exclusive, so add each individually, 0.16 plus 0.29, which is 0.45. And if you've realized already those two don't add up to 1, that's because there is an event C. If C is the event that the person chosen has normal cholesterol, which is below 220 milligrams per deciliter, what's the probability of C? So the probability of C is equal to 1 minus the probability of the other two combined. So we can do that, and that is 0.55. Hopefully you don't have any questions on it, but if you do, we can talk about it after we do 5.2B. So 5.2B is a really nice section that I like because I really like visual ways to represent probability. And today we're going to do the two-way tables and Venn diagrams. And then in 5.3, we are going to talk about tree diagrams. So this might be a little confusing for you at first, but when we do the sample problems, hopefully it won't be. So for each of these are scenarios. We are going to show visually what we're trying to represent. So in the first diagram, we have the probability of A. We have a two-way table and we have a Venn diagram. So let's just call A the right circle and B can be or A can be the red circle and B can be the blue circle. So if I asked you what is the probability of A, you would want to add this number here and that number there because that is all in the circle for A. So that includes the intersection in the Venn diagram is both A and B. So using the two-way table, that pound sign would be there, the number would be there, and then this represents the other one because this means A and not B. So that would be this little portion right here. So it's in A but not in B. And to figure that out, you would take those two numbers and you would divide it by the total. And the total would be here. And that's how I'm going to go through each of these particular scenarios. So the next one is probability of B. So the probability of B, so let's see, let's choose here. Okay, so this is B. So you would have a number here and a number there. And that would be, so the intersection is A and B. And here would be the other one because it's probability of B and not A. So you would add those two numbers together. And then you would divide by the total. It's not too bad, actually. I really enjoy the two-way tables. Okay, so for the next one, the probability that it is, the probability it's not A would be over here. Because we already know the A circle is on the right. And it would also be right there. Because anything outside the two circles would not be in either of them. So in the two-way table, where are those two pound signs? So the probability that it's not A would be right here. Because it's not A, but it is B. And then would be right here because it's neither A nor B. And then you would add those two together and divide by the total. All right, the next one, the probability that it's not B would be right here and right there. So not B would be this one because it's neither A nor B, and that one. And the total. When I teach this in Algebra 2, I really teach them with the two-way table because it really makes sense. Okay, next, now we're going to introduce some symbols from Algebra 2. The upside down U is an intersection, so it represents and. So the probability A and B is quite simply right here. That's where the intersection of the two circles are. So in that Venn diagram, and it would be this number right here, so only one box, and you would add that and divide by the total. Right. Next one, the probability of A or B, and this is if the events are mutually exclusive, and the right side U it means union, so or. So the probability A or B is just equal to the probability of A plus the probability of B. So it would be, and remember, if they're mutually exclusive, they can't happen at the same time, so the circles are separate. So you are adding that plus that, and so you have this number here and that number. And so you would add those two together because that one represents A and not B, and then B and not A. So you would add those two together. All right. And this would be null. Okay, so for the next one, if they're inclusive, meaning they can happen they can occur, you want to subtract that overlap. So you have, basically you have all of this, but you're going to have to subtract that middle region. So you're going to subtract this portion. So you have this, you have that, but you have to, so you have number, and then you have this as your number. That one is not that, it's not that very well represented with the two-way table, but I like it better with the Venn diagram. And then the last one, the probability not A and not B would be here. And that would be everything not in either circle. So it would be all of this. Because that is not in A, nor is it in B. And there you go. And that's basically representing all of those situations. And of course, when you're doing a problem in context, you would make your own two-way table or Venn diagram. Let's take a look at a couple of examples. So this first one, what is the relationship between educational achievement and home ownership? A random sample of 500 people who participated in the 2000 census was chosen. Each member of the sample was identified as a high school graduate or not, and as a homeowner or not. The two-way table displays the data. So if you look at the first column, it gives you the high school graduates. There's 310 of them. And if you look at not high school graduates, there's 190. If you add those two, you do get 500. If you look at the homeowners, there's 340 total homeowners and 160 that are not homeowners. That totals up to 500. So everything adds up beautifully horizontally and vertically. Look at the events that are defined. A is the high school graduates and B is the homeowners. Draw a Venn diagram to represent the relationship between these events. So let's draw a Venn diagram. Doesn't have to be perfect. Mine won't be, I know. Oh, that's really beautiful. That's okay. And so we can represent one of the circles to represent high school. And let's see, high school graduate, there's 310. And homeowners, 340. All right. And let's see, if they're a high school graduate and they're a homeowner, that's 221. So that is really crucial. Once we know what this is, we can figure out some other stuff. Well, we know there's a total of 310 high school graduates. So subtract 221 from 310, and that'll give you 89 here. And there's 340 homeowners. So subtract 221 from 340, and you get 119. Add those numbers together and subtract the overlap. So add 89 plus 221 plus 119, subtract any overlap, and you will get 71 here. Or just think of it this way. 71 is neither a homeowner nor a high school graduate, so that's going to go out here. But you have a total of 500. So the same information can be represented in a Venn diagram. It's whatever you prefer. Venn diagrams, sometimes students get confused with it. The two-way table, it's pretty easy to read. So we drew the Venn diagram, and now we're going to use either one to answer these questions. So the probability of A happening is, so that's being a high school graduate, is going to be 310 out of 500. And reduce your fraction. So that's 31/50ths. And you can go a little further if you want, and you want it in decimal, and it makes it easier for us to comprehend it. So that's 0.62. Okay, the next one, what's the probability of A and B? Let's remember this is A and B. So the probability, so that would be the intersection of the Venn diagram. So that'd be 221 over 500 equals 0.442. Okay, the next one, what's the probability of A or B? So here you can have them occur at the same time. So these are inclusive events, so you want to subtract off any overlap. So what you can do is find the probability of A plus the probability of B and minus the probability of A and B. It's always good to write these formulas in. Go. And so if we were to do that, the probability of A was 310 over 500, plus the probability of B is 340, because that's homeowners, out of 510. Oops. Oh my gosh, that's terrible. Over 500 actually, minus the probability that they're a high school graduate and a homeowner, so minus 221 over 500, and that gives you 429 over 500. If you would put it in decimal proportion form, like 0.858. On one of your worksheets, I do ask you to either put your answer in simplest as a reduce your fraction or round to 3 decimal places. Okay, the next one is what's the probability that it's not a number that represents not a. And so what you could do is you could just, the easiest way to do it is 1 minus the probability that it is a. And so that'd be 1 minus 0.62 from our first example. So that'd be 0.38. And the last one, don't be scared by this, but this means what is the probability? So this is or, but then you have the C outside the parentheses, so not. So that means not A or B. So the probability that it's not A or B is 71 out of 500, which is 0.142. All right, and for this last example, I will make a two-way table and a Venn diagram so you can see which one you like better. According to the National Center for Health Statistics, there's a website, in December 2008, 78% of U.S. households had a traditional landline telephone, 80% of households had cell phones, and 60% had both. Suppose we randomly selected a household in December of 2008. Make a two-way table or a Venn diagram that displays the sample space of this chance process. And I'll do both. So if we're going to do a two-way table, okay, so the events are landline and cell phones. So, and it doesn't matter which one you put where. Just if that's going to be cell phone, then this would be not a cell phone. But you could have written those two up across on the top, so it doesn't matter. And then here, landline, not landline. And it says, let's see, 80% had cell phones, so that would be out here, 0.80. And 78% had landline phones. And then we have one more statistic. It says 60% had both, so that goes right here. And I just changed all these to decimals. We don't want to deal with percents. We can't do any calculations that way. And then you can figure out everything else. So if the row adds up to 0.80, this will be 0.20. This would be 0.18. And then remember, the total is going to equal to 1 because that's what probabilities add up to. So this is going to be 1. So therefore, this would be 0.20. This would be 0.02. And this would be 0.22. So as long as you have one number inside the table, you can figure out everything else because you'll be given the other two pieces of information. Now we can do a Venn diagram, same information with really lousy circles. It's okay. So land, cell. Okay, so both would be right here, 0.60. Cell phone is 0.80, so this would be 0.20. And landline total is 0.78, so this has to be 0.18. And then out here is 0.02. Oops. A really bad drawing. Okay, and then you can use either one to answer the questions. Find the probability that the household has at least one of the two types of phones. So the probability that a person has a landline or a cell phone is, and you can use the Venn diagram or you can use your two-way table. So if you use your two-way table, then you would have to subtract the overlap when they do have a landline and a cell phone. So as long as you remember to do that, you're good to go. So the probability of just a landline is 0.78 plus the probability of cell phone is 0.80. Subtract the probability of both a landline and a cell phone. So it'd be 0.02. Actually 0.60. I don't know why I said 0.02. Looking at the wrong number. And that gives you a grand total of 0.98. All right, because honestly, we could have even done probability that it's 1 minus not land or cell. So we could have done 1 minus 0.02. And so here's another thing we could have done. There's so many different ways to get the right answer. It honestly is totally up to you and which method works for you and makes sense. Okay, part C. Find the probability the household has a cell phone only. So probability that's cell phone only. So cell, but not land. And so if you looked at your two-way table, it would be the top right because that's cell, but not land. So that'd be 0.20. If you looked at your Venn diagram, it would just be the right portion because it's in the cell circle, but not in the land. Lastly, find the probability that the household has no phone whatsoever, and that would be outside the Venn diagram or the bottom right of your two-way table. And the proper way to notate it is probability that it's not landline and not a cell. And so that's 0.02. And that just gives you a little taste of how to do probability calculations. We will continue to do more in section 5.3. Have a great day, AP Stat students.